Hi, everyone. Welcome. My name is Lyle Tavernier, and I'm speaking to you from NASA's Jet Propulsion Laboratory here in Southern California. Excited to be with a couple of colleagues today, and we'll be talking about how we observe the universe. So what is some of the science and what are some of the different scientific instruments that we use to do that? So I'm excited to hear more about that from our guest. Also, we're going to talk about how you can learn about some of the things we'll be talking about in the classroom or at home with some different activities. And one of the first things that I want to do, though, since we're talking about observing the universe and how we do that, is show you some new pictures. So the European Space Agency has a mission called the Euclid mission. They just released some new images. Maybe you've seen them. If you haven't, I'm excited to show them to you. If you have seen them, you probably won't mind seeing them again because they're pretty awesome. So what I'm going to do is pop up on the screen real fast, just a couple of these amazing images. So this is an image from the Euclid mission. Whoops, where'd my pointer go? I think I lost my pointer. Let me try this again. Oh boy. Well, I lost my pointer. I know it's somewhere around here. I'm trying to find it. There we go. Okay, so we've got this view of the spiral galaxy, IC 342, which is a great name for a galaxy. It's not quite as easy to say as the Milky Way galaxy or our neighbor, the Andromeda galaxy. But the Euclid mission is looking to study how things like dark matter and dark energy are making the shape of our universe and galaxies happen. So we're going to zoom into this one, and you can really see some of the incredible detail that these images have. This is that spiral galaxy picture that I showed you, but really, really zoomed in closely. There are a handful of other images. I'm not going to go into all of them, but this is the Perseid star cluster, and you can look at some of these amazing, actually, I think maybe star cluster is probably not the right word now that I'm saying it out loud. We've got the Horsehead Nebula. Again, you can see these amazing details in these images. And so this is the kind of stuff that is really the cutting edge of science. The European Space Agency, with some contributions from us here at NASA, have really put together an amazing mission. So I'm excited to see what other things come out of this mission as they study more and more of the data. So that's just to kind of get you excited, to show you some of the things that we'll be learning about in terms of making observations and studying the universe. But I want to show you how you can do this in the classroom as well. So students, we've got some activities for you. This is our NASA website, jpl.nasa.gov/edu. We'll pop that in the chat so you can have access to it in a little bit. But a couple things I want to point out. First one is the Learn section. So students, this is for you. If you want to do some learning on your own, we've got a lot of different topics, different videos and projects that you can work on. And what I'm going to do is I'm going to put a quick search term in the box here to bring up a couple different examples that are kind of important to considering what we're talking about today. I'm just going to type in the word black hole, and I'm just going to type in singular black hole because I found out today that if I type in black holes, I don't get as many good results. So a slideshow of different images from the James Webb Space Telescope. We've got a video about what a black hole is, and then another slideshow about black holes, just giving you some different information. So cool different stuff that you can check out here in the Learn section. Teachers, we didn't forget about you in the Teach section. We've also got a lot of different activities. These are all aligned to NGSS and Common Core Math standards. So there's things that you can just bring right into the classroom. I'm going to do a quick search for the word universe, and that gives me quite a few lessons that are really relevant to what we're talking about today. So how do we get the data back from these telescopes? What does it mean when we talk about the expanding universe? Lots and lots of different examples of how you can take what we're talking about today and bring it into the classroom. So I can see that Brandon put the link to that website already into the chat, so it's there ready for you. But I don't want to spend all day talking about those different lessons. What I really want to do is hear from Brandon about some cool experiences that he's had, as well as our guest Isa about some of the work that he does as well. So Brandon, I'm going to go ahead and turn it over to you.
Cool. Thanks so much, Lyle. Yeah, excited to share with you guys a little bit about some of the ways that we have worked on exploring the universe. So I'll kind of kick us off by talking a little bit about some of the work that I was able to do on things like the Spitzer telescope. So maybe I can share some slides with you guys. We'll get these nice and full screen. Great. So I'm showing you guys a photo now of a nebula that I got to study for 2 years. And as Lau pointed out, they don't get really cute names. So this one is called IC417. So it's a real beaut, much more pretty than the name might suggest. And if you guys can see my cursor here, if you guys can kind of imagine, there was effectively an explosion of some kind, maybe a supernova here towards the right of the screen. And maybe you can kind of visualize this being kind of like a bubble, like a cup moving outward. So you can kind of see the edge of the bubble from that force pushing all this nebular dust to the outside, right? And you can kind of see it doing it in 3 dimensions. The dust here is forcing contact with what is now effectively stars that are turning on for the very first time. So all these orange dots are brand new young stellar objects that because of the accretion, all that dust colliding is causing a change in gravity. They're all pushing together and they have ignited and created fusion, which is a wild, wild thing. So we're effectively watching a stellar nursery take place, which is really, really cool. Not quite for the this mission, but for another really cool program, I actually got to fly on what's called SOFIA. And SOFIA is a modified jet that flies, effectively at the stratosphere above all of the atmospheric water and light pollution and such that you can actually see into space much more clearly. And it looks like this in the air, which is, again, just a ludicrous opportunity. So, people who have used telescopes before will recognize the idea of putting a telescope in the back of a plane and then opening the plane so that it can see outward is a pretty wild concept, because if you've ever looked through a telescope, even like the most mild contact, you start to move around, right? You lose focus, you lose the ability to get a nice clear image. So how do you do that on a plane? How do you do it while it's flying, where you're just opening the door and a 3-meter telescope is out the side? Well, the way you do that is with an incredible array of stabilizers. So all of this ring here, these little, what look like little rubber tubes around the telescope are holding it perfectly in place, so that while we were on the plane, you feel the movement, but it stays perfectly still, which is kind of a wildly, uncomfortable feeling, because you felt motion, but something was perfectly stabilized. So the technology works, and then you can really be able to see, again, unhindered by water and any other chemicals that would absorb infrared light before they reach the surface. Interestingly, after all this work on SOFIA, on Spitzer telescope, and so forth, I was using the 2 images on the left. So I was using the WISE instrument and then IRAC on Spitzer, as well as a couple of ground-based surveys. And as I said, I worked on this for 2 years. And then James Webb came out and just produced this image. And effectively, all of my work was 2 years of work was done in a single photograph, which is, somewhat unsettling, but hey, that's science for you. That's how the game works. So, I mean, really, you can understand just how incredibly advanced James Webb is, and just these space telescopes are advancing to an incredibly wild degree. I mean, these images don't even look the same. As we were joking before the broadcast start here, these are effectively pictures that Lyle and I could take on the left versus our guest on the right here, and you'll see that soon. So before we hear more about photography, I wanted to kind of talk about the basics with you guys. And I think the first thing I wanted to convey is that when we use light to explore our solar system and beyond, a lot of these pictures you see contain information at different wavelengths, right? And the visible wavelength is in itself very nice, but not always the most informative. I like to tell students and teachers, I think it's really important we know that a lot of the images you see on the internet or on NASA or stuff like this, they're not just what you see with your eye. They're actually stacked images of multiple wavelengths kind of put together. So if you can see here on the bottom, this is one object at different wavelengths of light. So you can see it, like, again, looks very, very different with infrared, like I would see through Spitzer, versus what you would see in the UV or the X-ray. And each of those tells us very, very unique information. So, what is it that you're trying to glean is really, really important based, to determine what type of wavelength you want to use to study that object. Kind of pulling a very obvious talking point that you guys have no doubt heard before, right? Visible light, well, again, very easily accessible, represents such a tiny, tiny fraction of the electromagnetic spectrum. So think about all the other information that could be learned if you extend past just what you can see with the naked eye. Just as an example to kind of demonstrate this, this is a panoramic photo of, effectively our sky, this beautiful shot of the Milky Way. And this is what it looks like with the visible light. So if you were in perfect darkness, much like Isa and I were earlier this year when we were in Chile, out in the middle of the driest desert in the world, at altitude where, again, you could kind of escape light pollution and atmospheric interference, if you spent all night, you could get a photo just like this one. And while this is beautiful, and again, has a lot of cool information in it, it doesn't tell us as much information as we could gather, again, if we also looked at other wavelengths. So similarly, you can take a look at the infrared and you get an image like this one. Now, again, this looks maybe a little haunting. It looks very like Eye of Sauron kind of scary image, but you can grasp at an instant, right? Like very, very different information is contained here. So why not? Why not kind of put these together in multiple wavelengths and collect and stack and have a complete picture beyond what we can see? There are a bunch of really neat resources kind of demonstrating this. This is a great, just kind of final point. If you take a look at the image on the left, this is in visible light. A very common picture that you see. I remember this used to be like preloaded on every computer desktop as like the prototypical beautiful image. And I remember getting to JPL, and just in the first couple of weeks, a scientist told me how much he hated this picture because it represented to him a failure of not being able to see everything that was behind that dust, right? So very, very pretty in the visible spectrum, but all this dust, this beautiful nebula, is, however, blocking information on which stars are behind it. Thus, on the right, you can see the same image in the infrared, and now all of a sudden we can see through that cold dust to the hot stars beyond it. And now all of a sudden, right, again, we have a full catalog of stars to explore. There are a bunch of really great kind of sliding scale images of this on the NASA webpage. I put a link there at the bottom. So you can imagine if you wanted to kind of see in multiple wavelengths, again, side by side, you can slide these over to get a feel for what information you might be able to grasp at different wavelengths. Now, you might be asking, well, how do you see at different wavelengths? One of the ways that we do that is with what's called a filter. So you put a filter on your telescope. And again, people who are much more familiar and working with astrophotography will recognize that different filters allow different light to come through. Ideally, you want this kind of shape here, this kind of top hat shape, where like it's a nice clean cut and it's only going to let these type of things in. If you see like Sloan R versus R here, right? Not super relevant as to what filter does what, but this allows red light through. And you can see the Sloan one really lets in a clear line here, whereas this guy has like a long tail. So all of a sudden, all this extra light is going to come in that's not even in the visible light. And you start to get some bleed, right? You don't have the nice, clear, sharp edges that you would like. Which is interesting because when we apply these filters, we can actually kind of imagine what types of stars we could let through. And I want to kind of model that for you guys for just a second. So let me stop sharing here. And what I'm going to do is, let me put myself on the stage. What I'm going to do is just kind of, imagine with me, if I had several different stars, a red star here, ooh, look at that, a lot of vertical brightness there, and a blue star here, like so, got two stars. If I think back to that image of IC417 that I showed you, or any of the other images afterwards, how many thousands of stars were on that? Now, if I only want to see those young stars that I mentioned, those ones that are just turning on for the first time, a young star is by definition one that is just, is effectively blue, right? Now, the converse isn't always true, but if I see a blue star, I know it's young because it's big, it's hot, and it burns out quickly. Blue stars don't live very long. So if it's blue, it must be young because it's still there, right? Red stars tend to be older, colder, this type of thing. Think of the temperature of your maybe gas stove versus that of a match, right? Those blue ones are hotter and burn brighter. So now I've got these two stars, but I only want to see one versus the other. The best way to do that is to apply a filter. So what I'm going to do is I'm going to hit the lights and we'll take a look side by side. Okay, so maybe we can see these nice and bright. Cool, cool. And if I want to, again, only see my blue stars, well, what I'm going to do is apply a blue filter. Make sure they're both on here. There we go. And now I can effectively turn off the red ones, but keep the blue one on, right? So all I'm doing is covering my camera with a filter that allows me to select which one I see. Similarly, if I wanted only the red stars, I don't, but maybe someone else does, I can apply a different filter and turn off the blue ones, right? Like so. So you can see here selectively, we can decide which stars make it through the filter and therefore allow us to kind of analyze exactly the ones we're looking for. Pretty cool. So let me close out by saying, before we turn over to Isa, that as mentioned, I might not actually be doing this in visible light. Maybe I'm doing this in infrared versus visible, and that might look something like this. So this is a cup full of ice, and what I'm doing is I have an infrared camera on it, and if I put a plastic bag over it, maybe some stellar dust, if you will, you can still see that it's cold through the bag. But using plexiglass, which is a filter, I can turn off, if you will, being able to see the temperature of the cup in the background, which is pretty cool to think about. So, again, this is how we use light to study across different stars and the sky and so forth. But you can imagine, not everyone has a giant space telescope or right an all-star survey. So to this end, I wanted to invite my colleague and fellow travel partner, Isa, who traveled with me to Chile this past year and is an incredible astrophotographer. So maybe he can tell us a little bit about how to collect pictures and how we can get awesome images of the stars down here on Earth. So with that, Isa, please, would you mind enlightening us and take it away?
Hey, Brandon, thank you so very much for the introduction. Thank you to Lyle, and I'm so happy to be here with you guys this evening. So I'm an astrophotographer, and I'm from an island in the south of the Caribbean called Trinidad and Tobago. And I'm going to show you guys just a little bit of what can be done without the big professional observatories, without a NASA-sized budget. What could really be done from your backyard. You see, I'm not a professional astronomer. I'm an amateur astronomer and astrophotographer. Yeah. So let me share my screen. Get my, here we go. All right. So you guys can see this. Yes. Yeah, great. Okay, so just a little bit about me. My name is Isa Mohammed. I'm president of the Caribbean Institute of Astronomy, which still it's a volunteer organization. So I am an amateur astronomer and I'm an astrophotographer. Astronomy is my passion, and I spend a lot of time teaching people about the sky, showing people through telescopes, doing presentations such as this. But astrophotography is the part of it that I really love the most, and that's what I'm going to share with you guys today. Just a few of my photos and just a little bit about the process that gets you to make one of these photos, right? So this is an example of a nebula. This one, we do have the funny numbers, but us astrophotographers in the amateur astronomy community, we like to put whimsical names for our nebulae. And this one we call Thor's helmet. So this nebula is Thor's helmet. You guys, I mean, I hope you could see what leads it to be called that. But coming hot off the heels of Brandon's presentation, I want you to notice that there are two different colors in this image. There's it's really a sort of cotton candy, but a cotton candy pink and a cotton candy blue. And the reason is because this image was acquired through different filters, right? And there's a filter that selects for hydrogen, the hydrogen alpha emission line, and there's another filter that selects for oxygen, the oxygen 3 emission line. Now, both of these are caused by the excitation of particles in a cloud by light coming off from stars. The result is that it glows in different parts of the spectrum. And when we could use filters to create images, we could highlight where certain molecules are located in an image versus where other molecules are located. And even us amateur astronomers with the filters that we have, we could create an image like this that is not only beautiful, but it also has a bit of that scientific context in it. Where are the different molecules? And in this case, the hydrogen molecules are where you're seeing pink, and the oxygen is where you're seeing blue, right? Astrophotography is a bit of a technical art. So there's a technical side of it, but at the end of the day, what we're trying to do is create a beautiful image. So there's an artistic side to it. It's something we want to be able to move people, to create an impression. So here's another one. IC410, we have the name, but again, it's amateur astronomy. So this we call the Tadpoles Nebula. The Tadpoles Nebula. I hope you guys could see again why we're calling it the Tadpole Nebula. It's those two globular formations towards the upper part of the middle. And again, we have the same thing going on here, where we have the blue area and we have the orange, and the orange is more the hydrogen. The blue is more the oxygen. But in addition to that, in this one in particular, you could see those brown areas of that's dust, that's interstellar dust, and that's between us and the nebula in the background. You can see it sort of sits between us and the stuff in the background. And that's the sort of thing that an infrared telescope would be able to see straight through, right? And I think Brandon demonstrated that in his presentation. But here we want to capture that dust and show where it is, and it's part of the composition of the image, right? This one we call the Bat Nebula. Now, this one is a supernova remnant, and it's the material that was left over from the explosion of a star in a supernova. And this is just one small part of it. It's a big shock wave. It's a giant ring in space, and we're zoomed into just one small part of it. But you could see the different colors. You could see the hydrogen. You could see the oxygen. But in this one, there's a third color. There's blue. Where's the oxygen? There's red, where's the hydrogen, and there's pink towards the upper right-hand side. And that's actually a third emission line, that's sulfur 2. Now, in amateur astronomy, those are the three, when we're doing narrowband images, those are the three most prominent lines that are visible to our instruments: the hydrogen, the oxygen, and the sulfur, right? But it comes together in a beautiful image, sort of like this one. Now, apart from the nebulae, we could also image other targets in the sky. This one is the planet Mars. I captured this in 2020. Again, this is the sort of detail, if you have a good telescope, if you have great conditions, and if Mars is at the point in its orbit where it's really close to the Earth, you could capture an image like this that shows you this much detail, where we have mountains, we have volcanoes, we have canyons, we have all the albedo features, which are areas on the surface that are darker, that are lighter. And we have, of course, the polar ice cap. You can see the top left hand of the image, that white smudge there. That's the polar ice cap on Mars, right? So Mars is an interesting target because there is a thin atmosphere, and there's oftentimes little changes that you could get. You could pick up dust storms sometimes. Sometimes you could see cloud features. But again, this is the sort of thing that's within the reach of amateur astronomy. Similarly with Jupiter, and Jupiter has a wealth of surface detail that you could see in its atmosphere. There's a lot of turbulence, and it's always shifting, always changing. Now, stepping outside of our own galaxy, we can actually image other galaxies. And I most I most believe Lyle would have mentioned earlier, he said star cluster, and he thought he made a mistake. He's like, no, it's not really a star cluster. No, that was a galaxy cluster, Lyle. I caught that. It was a galaxy cluster. Now, this is an example of a galaxy. This is the Triangulum galaxy, Messier 33. And this is an island universe out in space. It's completely outside of our own galaxy. These things are hundreds, sometimes thousands of light years away. Each one of these contains hundreds of millions of stars. And you could actually see in here, those red blotches are nebulae inside of this galaxy that is outside of our galaxy, right? So those red splotches that you're seeing there are actually nebulae or star formation regions inside this other galaxy, right? Here's another example of a galaxy picture. This is the Sculptor galaxy, so-called because it's located in the constellation Sculptor. And as Brandon would have mentioned, if you go to a dark site and you could look up and you could see our galaxy, the Milky Way galaxy, this is me attempting to capture what Brandon and I saw when we were in Chile together. This is the Milky Way galaxy as viewed from the Chagnantur Plateau in the Atacama Desert in Chile, where the ALMA telescope is located. And this is our galaxy, the Milky Way galaxy, seen from the inside. So we're inside the galaxy, looking through it. And that orangish bulge towards the middle, that's the center, where the center of our galaxy is located. And those dust lanes, we are embedded in part of that. The galaxy is a big disk, and we're inside the disk looking out. And that's what we see. So guys, these are some of the types of pictures that you could take with amateur type equipment today. And this is a telescope that I use for most of the images that you would have seen there. It's a 10-inch reflector telescope. It has a CCD camera hooked up to it with a filter wheel, and we'll get to those filters in a second. And it's on an equatorial mount, which allows it to track the rotation of the Earth. And this type of equipment is within reach of amateurs. I wouldn't go so far as to say it's completely inexpensive, but it is within the reach of serious amateur astronomers. And so amateur astronomers today with equipment like this could take images or image the sky in a way that professional observatories could not even do just a couple of decades ago, right? So we've caught up to where professional observatories were just 20, 30 years ago, using effectively off-the-shelf equipment, right? But it's not point and shoot. You don't take your telescope, point it at the sky, and get an object. And this is true of the professionals as well as the amateurs. So this is where we need to use some of the techniques that the professional astronomers use. On the left is what an image looks like when I get it off my camera. It's a mess. You barely see anything. It's got vignetting. It's very noisy. It's in black and white because these cameras are monochrome. They're not in color. You can get color cameras, but you know, there's a reason that I use monochrome. When you apply your calibration to the data, you get something on the right. You get something more flattened out. Most of the gradients are gone, and you could start seeing something, but it's not quite wonderful yet. You see, the objects we're shooting in the sky are very dim, and you have to shoot lots and lots and lots of them to get a good image. We use a technique called stacking, where we take hundreds of images like what you see on the left, and you average them together, just using mathematics, just average. You average them together, and you get what you see on the right. You increase the signal to noise ratio of the image, and you're able to bring out all these faint details and drive down that noise. And this is the technique. It's called stacking, and it's what amateur astronomers use to get good images of the night sky. And this is filters. Brandon spoke about filters. Here is my filter wheel on the left-hand side. So those are what the filters in an amateur telescope CCD camera look like. We have blue, red, and yellow, of course. And then the other three that look silver, those are the narrowband filters. Those are the hydrogen alpha, sulfur, and oxygen 3 filters, right? And the seventh one is just a clear filter. But you take images through these filters and you combine them to get a color image. So you would take a red filter, a green filter, and blue filter to get a natural light image like the galaxies I would have showed you. Or you could combine the oxygen, hydrogen, and sulfur to get what we call a narrowband image, like the nebulae images I would have shown you before, right? So this is what a final galaxy image in red, green, and blue would potentially look like when we've gone through the whole process of calibrating, stacking, and combining different colors into one image. And these images typically take me, honestly, weeks to produce, because I would spend dozens of hours collecting data night after night after night, and then several days combining it together into a final image. And this is the last one I'm going to leave you with. This is the Horsehead Nebula. Lyle would have showed us a much better image of the Horsehead Nebula from the Euclid mission. But this is my rendition of the Horsehead Nebula. And I'm leaving you this one at last because I think it really showcases that astrophotography is not just science, it's not just technical, but it is an art. And it's meant to create images that are beautiful and images that are moving. And this is one of the favorite ones that I've done that I feel really captures the spirit of that. So that brings me to the end of my bit. Gentlemen, thank you so very much. Back to you.
Thank you.
Incredible. Yeah, absolutely amazing.
Wow. Yeah. I just want to quickly comment on the fact that the Euclid mission required a telescope in space to take that image. And you got that beautiful image with your telescope here on Earth. So absolutely incredible. Amazing. Thank you so much. So Brandon's going to lead us through some Q&A. So if you've got some questions about what we've been talking about today, some of the things that Isa told us about, please put those in the chat. Our chat is sort of limited. So since Brandon's going to be leading the chat, I'm going to ask you to put the chat questions in directed to him rather than me. That way I don't have to tell him the questions, and it'll just make things go a little bit quicker that way. So Brandon, I don't know if we've got any questions yet, but I just, again, Isa, thank you so much for sharing your images.
Yeah, I mean, truly works of art, and yeah, not quite where Lyle and I are yet, but we're gonna work on it. You're gonna motivate us.
Oh, it's my pleasure, guys.
Well, we have a ton of questions, of course. I think the very first one is, about, again, stacking. Is that software kind of easy to navigate? Is that, they've done all this work on taking pictures. They have to be software developers too, or what does processing look like?
Yeah, I'm not gonna lie about it. It is a bit technical. So there is software involved. But there are different levels to this thing, like there are to everything else, right? And there's some ways to do this that are easier than others. You don't even have to stack if you don't want to. If you live under really dark skies, right? Where I am, I have a lot of light pollution. So I really need to stack to get good images out. But if you live under reasonably dark skies, I mean, you could literally take your camera DSLR and do a slightly long exposure and get an image of a nebula without having to stack, so you could get into it at the level that you are. But if you want to take it all the way, yes, it does get complicated. The software is available and it's good, and there's a lot of information out there, both on YouTube and also on discussion forums. Cloudynights.com is a fantastic resource, and there's a lot of information out there if you really want to get into it. But you don't have to be a programmer or a developer. The software is really good. It's stable. They're making it easier and easier to use all the time. So, I mean, if you're familiar using stuff like Lightroom or Photoshop or anything like that, then I suspect you'd be fine.
Awesome. A couple people are asking too about some of the young stellar object stuff, like particularly around the size of the stars. And let me tell you that I showed you a red star versus a blue star. Blue stars are actually also bigger. So bigger, unique color makes them really, really easy to find. But this is a question from Theodore. You're absolutely right. Small stars are actually very, very difficult to find. And that's just a feature of trying to look at things that are so far away, right? IC 417 is 2.3 kiloparsecs away. I mean, it's just so distant from us that, any small object we can't see. So a lot of times we just take the best image we can get, right? and bigger, brighter things just happen to be easier. So we have a little bit of a sampling error, if you will. It makes the universe look like we see more big, bright things, but those small things are there, and we're catching up and being able to detect them more and more. Yeah, so this is a good question for you, Isa. So, thinking about different filters, there are these images coming in from other, exoplanets and stuff like this indirectly. Do you think we will ever get to a place where an amateur astronomer could actually see like exoplanet features? Will you ever be able to like see something that small across a star?
Oh, no, I mean, but technology is moving, so I'm not gonna say that it's never gonna happen. But resolving detail like an exoplanet is really, really difficult. Even professional telescopes today cannot resolve detail on an exoplanet. We've gotten to the point where we could resolve detail on objects as large as a star, right? And Brandon, you and I saw that when we were at ALMA. They showed us a beautiful image of Betelgeuse, right? And there was detail on the star. A star is a lot bigger than an exoplanet. What we can do with amateur level equipment is detect the presence of exoplanets using the transit method. So we could detect when an exoplanet travels in front of a star, the brightness drops just a tiny bit. And with amateur level equipment, we can detect that. So we could plot the light curve and we could detect the presence of an exoplanet. But to be able to image an exoplanet, it's really, really difficult. Only a few telescopes in the world are able to do that right now. But like you say, technology moves on, and who knows, one day maybe that sort of thing will be within the realm of amateur astronomy, but it won't be soon.
Yeah, I mean, that would be a huge step forward. But then, I mean, imagine what assistance the citizen science community could be to science overall. Because again, we're looking, the sky is just enormous and space just goes on forever, guys. So like, the images you've seen are such tiny, tiny little pixels in the sky compared to the entire galaxy out there. So another question for you, actually, speaking of, of what we can see, Henry's asking, are all galaxies the same shape? Are they all round? You've showed some images of kind of fragments of supernova and stuff, but what kind of shapes do we expect in galaxies out there that we can photograph?
They broadly categorize galaxies into three categories. They are your spiral galaxies, which are the really beautiful ones, right? The ones that have that whirlpool spiral shape. There are elliptical galaxies, which are the ones where it's basically round. And then there are irregular galaxies, which are ones that have really distorted shapes. And you, as an amateur astronomer, you can photograph all three types. There are spirals, there are ellipticals, and there are irregular galaxies, and all are able to be photographed by amateur level equipment. Me personally, I enjoy shooting the spirals, so I don't have a lot of examples of the other types, but they are certainly well within the reach of being imaged by amateur level equipment.
And a couple people are asking about the supernova side of things too. So maybe you could tell us a little bit, like, how do you find the remnants of a supernova, and why is it that we can't, see it effectively taking place, right? Why do we always see history, right? Maybe you could kind of talk us through those two things.
Oh, no, I mean, it's not actually true that you can't see it taking place. Amateur astronomers image supernovae all the time. In fact, in many cases, amateur astronomers are the ones who detect when a new supernova is happening, because so any random amateur astronomer is imaging the whirlpool galaxy tonight, and suddenly a star appears that's not supposed to be there. So in your data, you'll see that there's a star, and that star is not supposed to be there. And what that is, you normally cannot see stars in other galaxies. So if you are seeing a star in another galaxy, what you're at, especially one that's not supposed to be there, you are seeing a supernova taking place, right? And then the call goes out to the astronomy community, guys, there's a nova or a supernova in so-and-so galaxy. And then it's like hundreds, thousands of telescopes all around the world, both professional and amateur, suddenly tune in to image this thing. And then we get measurements of how bright it is, and it's getting brighter and brighter every night. And then after days and weeks, it starts dimming off, and you can plot that entire curve as the thing brightens and crests and then slowly fades out. So we absolutely do see supernovae in other galaxies all the time. What's not so common is seeing a supernova that's really close to us in our galaxy. But it does happen. About 1,000 years ago, there was a supernova bright enough that it was recorded by ancient civilizations all across the Earth. And this story sort of segues to answer the first part of your question, right? There were all these reports of this star that was visible during the day, right? It was so bright, it was visible during the day for months. It was blazing in the daytime sky. And there were reports of it in many, many cultures. And astronomers, what they did, they looked back in these historical documents and tried to figure out where this mystery star was. It appeared and then it disappeared. They tried to figure out where in the sky it was. And then when they sort of had an idea of where it was, they pointed a telescope at it and they imaged that spot. And what they got, or what they found, was a nebula that we call the Crab Nebula. And now we know that it's a supernova remnant from that explosion that took place 1,000 years ago. So that's an example of how that one was found. But other than that, scientists do surveys of the sky specifically to find these objects. We don't know where they are. The sky is huge, and these objects are in a tiny, tiny place in a massive, massive sky. You really can't just randomly look at a patch of sky and expect to find something. It really doesn't work like that. You need to pinpoint where you're looking. And so part of the job of these big professional telescopes is to map the entire sky and look for anything new that could be, for example, an undiscovered supernova remnant. And then sometimes amateur astronomers are the ones who discover them, because we're crazy enough to spend, 5 months imaging just one part of the sky, which is something no professional astronomer would do, because nobody has the time to spend 5 months on one part of the sky. But then an amateur astronomer, because they've spent so much time on that one part of the sky, they discover something that nobody's ever seen before. And new supernova remnants have been found like that by amateur astronomers.
That's incredible. We have time for probably one more question. I know it's a tough one, but to the best of your knowledge, how far into the sky have you been able to see, or amateur astronomers been able to see? Just for the audience to be able to kind of feel for how deep we can see.
No, actually, it's a really good question, and I'll tell you what the furthest object that I have observed is called OJ 287. It's a quasar, and it's located 5 billion light years from Earth. And that's the furthest one that I've personally imaged. I did observations on OJ 287 as part of an observing program in conjunction with the University of the West Indies. I ran the telescope, I made the observations, and that object is 5 billion light years away. It's basically a third or half the way across the entire known universe. So the answer to that question is that we can see as far as the edge of the universe. So I guess we call it the observable universe because that is literally as far, that 13, 14 billion light years away is about as far as we could see. But we can see pretty much, billions and billions of light years away.
Yeah, this is just incredible. Really, really just so impressed by what skills we can develop. And of course, the science being done at NASA is amazing. But yeah, again, don't wait until you have the job. Get started, right? Start playing with the telescopes now, and fall in love with the sky now, right? I think there's no reason that it has to be a career goal later, because I think it's there's so much we can learn, there's so much we can share, and looking at these images, just like Isa said, right? You have to appreciate the art of it. Really incredible. So with that, let me turn it over to Lyle to close us out, and I think we'll wrap up.
Great, thanks, Brandon, and thanks, Isa. Appreciate both of your inputs on all of these really cool topics. To everybody watching today, I hope you learned a lot. I hope you got inspired. And yeah, just as Brandon said, you know, it's never too early to fall in love with the sky. It is the most accessible astronomy that you can do. You can just walk outside and look up at the night sky. I hope to see some of you in the future here at NASA. Hope to see some of your future astronomy images that you've taken from all of us at the Jet Propulsion Laboratory and NASA. Have a great rest of your day. Bye, everybody.